Okay, welcome folks to another session. Uh, Hopefully today should be the last session on logistic regression. We've done quite a bit so far. Uh, I don't. I hope this session doesn't take about the usual an hour and 30 minutes. It could be much shorter. All right. So let's
Class.
get. Sorry, was that a question? All right. All right. So let's get. Sorry, did somebody message? All right. Oh,
No,
Pavitra.
no, please ignore, please ignore.
All right. Okay. I'm back. So you're announcing that you're back. All right. All right, cool. So let's continue from where we left. Uh, do we have Sirisha here? If not, then I can use some Tamil words. Yep. Okay. Sari. So பழைய குப்பையை நம்ம திருப்பி கலருவோம். Uh, I hope this expression. Okay. I think let me do what Sandhya suggested. Give me a moment. Pointer. It's useful. Yep. So I hope this expression rings a bell. What does this expression say? It basically says that you take a data point, an example, and then you can try to figure out the cost, and then you calculate the partial derivative of the cost with respect to Wj. Then you have this expression, and we know that this bit is y hat. So you can write this as y hat minus y multiplied by xj. So that would be the partial derivative of the cost function with respect to Wj. Now, that was just one data point. Let's try to expand this to m data points. So let's say you have m data points, and then here is the cost function. Earlier, we were looking at just one data point. Now we're looking at m data points, and here's the cost function. What are we doing here? It's nothing but it's simple. You take each uh, example or each row, you calculate the cost function, which is LCE. Then you sum up the cost functions of all the examples and then take an average. So this is essentially means you're summing up the cost. Of course, it's a cost function here. And then you're dividing it by the number of examples, which is m. All right. Now we know how to calculate the cost. We've already done that before. So it is nothing but we know it's y times log of sigma, or let me put it this way, y times log of y hat plus 1 minus y log of 1 minus y hat. We've done that before. All that we're changing is we're just replacing y with yi because there are m data points that you're going to deal with. Earlier, we were dealing with one data point. Now you're dealing with m data points. So we just put this superscript yi, and then so this is, imagine this whole thing to be the cost function for one example or one data point, if I may say so. You sum it up and then you divide it by the total number of um, data points, which is m. All right. Now, once you take the derivative of this is the expression that we get. Now, can somebody help me to? I don't want you to derive this expression because that's not the objective here. But can somebody help me to understand? I mean, given that we have already derived it for one example or one simple cost function that we derived using one data point, can somebody help me interpret this expression? You can draw inspiration from this expression here, the one on top. Either which can somebody help me interpret this? Just have a nice look at this expression, which was the derivative, the partial derivative of the cost function. Of course, the cost function was derived using one example with respect to Wj. This is again a partial derivative, but then what you're doing is the cost function is summed up across examples. So can you just help me interpret this? What is this? How are we supposed to interpret this?
We see if we take like x1, x2 to be like some 2, 3 and y to be 0,
No,
we can say
let's not get into specifics. So see, there are okay, x is a vector, so there are features. Let's say there are x1, x2, x3, x4, x5, x6 features. All right, so 6 features. Then you have a lot of data points. So something like, say, let's say there are 6 features. All these are data points, and then of course you have a y, which is this column. So you've already, for a given set of feature values, you have figured out how the record has to be classified. All that is there, but my question is different. What I'm asking is, how do I interpret from here? How did I get to here? Let me put it in a different way. From here, how did I get to here? This is something that we already did. How can you make use of something that we already did and move to this? Just have a good look at this, folks. Is it that difficult? Someone give it a shot.
We see. Actually, what are you expecting? Like, what do you mean by interpreting it? I can't understand.
Okay. We have this, something that we've already derived, and then we have this expression, right? This expression is for m examples. Now help me to derive this, given that I've already derived this. You understand my
We
question?
see we got y cap minus y into xj. The
Okay.
term by deriving minus y log sigma of x double y sorry wx plus b minus y, right? Sorry, let me keep it simple.
Mm-hmm.
So we derived uh, the first term dou lc divided by dou yj
Mm.
with given lec is equal to minus y log of y hat minus 1 minus y log of 1 minus y hat, right?
Okay.
So the cost is nothing but the average of all uh, the LCE is loss of one feature, say one variable, but the cost is the average of all the variables in the data set. If
All
the
the
derivation
variables
of
or
the
all the examples? What do you
all
mean
the
by
data points,
all the data points? Okay, go ahead.
so the cost function is the average of all the data points. So the derivative of the cost function will be the derivative of the losses average.
Okay, go ahead.
That's
Is
why
there
we got
so so
summation
so
and
so
1
if you
by
look at this, this
SB.
exactly mimics this, right?
Yeah,
There's no difference at all, correct? The only
SBC.
difference between this and this is you've taken this and you're summing it up
SBC.
across
It's
examples.
an average that's for a
Exa-
single
Exactly. So
data
this is
point.
for one data point, which means like one single row. Here you have computed it for m different rows. So basically you've computed an average. Okay. Now, I'm going to take an example. The objective is not to go through a lot of mathematics. That's not the objective. But see, sometimes when you see an expression like this, and when you try to implement, which is why I strongly recommend that you implement stuff. Just staring at equations is something, and then getting to write a piece of code and then attempting to solve it is something else. So sometimes when you look at this expression, and if you try to implement it, you might get confused. What do you average, for instance? So let me ask this question. So here we have an example. We have 6 features: x1, x2, x3, x4, x5, x6, and then you have the bias as well, which is b. I'm calling this as a new feature whose value is 1. All right. Why do I do so? Because instead of, I can do it this way, right? So instead of z is equal to w dot x plus b, I'm just writing it as I will add another feature whose value is always 1. So it's like plus b into 1. So effectively, my features are the x vector plus that 1 vector. And the weights are the w and the b. I'll put all of them together. So usually when you do neural networks, typically you would call this as simply w dot x, because what you would have done is you would have included the vector 1 as a feature in itself, and then b of course would be its weight. Okay, but that's not the objective the objective behind why I wanted to show this. So here are, how many data points are there? We have 10 data points. I have weights. I'm starting with some weights. Here we go. So you have 7 weights, which includes the weight of b as well. I'm calculating z, which is nothing but w dot x plus b. Now, once I have z, I can calculate y hat. It's 1 by 1 plus e power minus z. I have y. Then I'm calculating y hat minus y. Okay. Now I have a question. Let's go back to this. I have to do an average here. So this is nothing but, if we choose to interpret it, let's write it down. So I'm going to write this again. So 1 by m times I is equal to 1 to m, and in bracket, I'm just writing it as y hat minus, sorry, I'll call it yi hat, okay, minus yi times xji. Maybe I will just give me a moment. I'll redo this so that the nomenclature is clear, or rather the notation is clear. Okay, so let's just call, I'm going to call this as yi hat, okay, minus yi times xj I. Okay. So I is essentially, it's a reference to a row or a data point, reference to a or an example or a row, whatever you want to call it. Okay. Example, row, data point. Okay. Now, the question that I have is, so in our example, m is equal to 10. I think we understand that. Why? Because there were 10 rows. Now, can somebody tell me how many so there's a xj, right? How many values can j take in this example?
1 to 6.
Can we include this as well? I can also take that, right?
Yeah, we see.
So essentially 1 to 7, correct?
Yes, yes.
All right. I can call this x0, for instance, something like that. It's just that it's a constant value of 1. Okay. All right. Fine. Now, so certainly this says that we're going to average something. We're calculating yi cap minus yi, then multiplying it by xj, and then doing some average. So my question is, do I need to average the x, the individual x, or do I need to calculate this whole expression and then average it? You understand the difference? So for example, do I need to take this, take an average, this, take an average, this, take an average, and then compute? So for example, let's say I have my y hat. So do I need to take an average of y hat, an average of yi, and then average of xj, and then compute this expression? Or do I compute this expression for each row and then take an average? Or will both of them
The term and take average.
or will both of them remain both of them be the same?
I guess it's no use.
Sorry, say that again.
I guess both of them are not same if
Why?
we take average.
Why?
If we take average like y cap into xji minus the average of yi into xji, it will be same, but not the multiple. I don't know the summation. The multiplication rule will
Okay,
be
fine.
applied to.
Okay, fine. Let's not worry about it. So according to you, you compute this expression and then you take an average, correct? Is that right? That's what you're trying to say. Okay. So let me ask a question. I'll take one row and I want to compute this expression. How many such expressions would I calculate per row?
7.
Okay, 7. I want someone else to answer. So when I'm calculating 7 expressions per row, what will change in that row? So this is the expression. I'm going to calculate 7 because Sandhya suggested there are 7 features here. Of course, x0 is a feature whose value is 1 throughout. My question is, when I'm computing, I take one row and I'm looking to calculate this expression. What is it that will change when I calculate this expression against that row?
xj.
Exactly. So xj is the only thing that will change, correct? Y I hat minus yi remains the same. That doesn't change at all. So if you look at, so what we've done here is we have yi, I mean, I'm calling it y hat here, but this is actually technically y I hat, because I is with reference to an example or a row. All right. So here we go. So you have y hat or yi hat. Then you have yi. Figured out the difference. Then if you look at this, it's x1 times y hat. I mean yi hat minus yi. This is x2 times yi hat minus yi. Again, I'm using the word I here because, or rather I'm using the letter I here because I'm referencing row number 3. So I here is, or rather, let me put it this way. I'm just calling this first data point, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. I'm going to call this as I for convenience. All right. So if you look at this, I think it was Purnasri who answered it. You're right. What changes is xj. The rest remains the same. Nothing changes. You're still using the same yi hat minus yi. All right. Now, the next question that I have is, are you going to sum all this and then divide it by average, or you're going to sum each of these columns across rows? Understand my question? Are we going to sum all this? So there are 1, 2, 3, 4, 5, 6, 7. Are you going to sum this and divide it by 7? Or are we going to sum this and divide it by 10? What are we going to do? Look at this formula and tell me.
Summing the column divided by 10.
That is right. Correct. So what are we doing here? You sum up this and divide it by 10. Okay. So what I've done here is basically taken the average of all of them. Okay. Now, going back, I have figured this out. I've done this for each of the, so if you look at it, I would have calculated this for each of the wj. So w1, w2, w3, w4, w5, w6, and of course b as well. All right. What is the next step? I've calculated the average that we need, but what is the next step? How does the optimization algorithm work? After I've calculated the partial, sorry, say that again.
Updating the weights.
Exactly. So how do you update the weights? So if you take the general expression, this is a general expression to update the weights, right? Correct?
Previous weight minus learning rate into
The derivative,
gradient.
correct? Okay, all right. So here is, I have plugged in a learning rate. I fixed it. It can be any learning rate. Typically, when you play around with it, you have to play around with multiple learning rates. I've just plugged in 0.1. So first step is to figure out this expression, eta times, eta being the learning rate. This, of course, this whole expression is for one variable, which is why you see a D and not a DO. All right. Had this been multiple W's, then you would have seen a DO by DO W1, DO by DO W2, so on and so forth. Okay. But I think it's a useful expression for us to understand how weights are updated. So you have eta multiplied by this derivative, correct? So which is what I've done here. I'm calling it delta W1 just to say that it's a change in weights. Okay. And how am I computing it? It's very simple. I've already figured out this is the partial derivative that I've already figured out. I multiplied by learning rate to calculate delta W1. Then again, partial derivative, I figured it out, multiplied by learning rate. Again, the same thing. Finally, delta B as well. What's the next step? Now that I've figured this out, I figured out delta W1, delta W2, delta W3, delta W4, all the way up to delta B. What's the next step? Have a look at the spreadsheet, folks.
Subtract W and delta W1.
Exactly. So what do? You start updating the weights as, sorry, who was it who said that? I think it was, I forgot. Somebody said that. Yeah. So we update the weights. And as Mugundan just said, I already have the initial weights with me. I've figured out the deltas. So the next step is to update the weight. How do I do that? I take the initial weight and then I subtract the delta. So this is my new W1, then new W2, new W3, W4, all the way up to, in this case, delta B. So which means I update B. Now, once I've done that, the show begins again, where I again take the same data set, but now I apply the new set of weights. Okay. Of course, there is one thing that I didn't do here, which is I'm supposed to figure out the cost after I get the new weights. I haven't done that, but what you would typically do is you would look at you'll calculate the cost once you have the weights, and then you repeat this process again and again and again till you reach a stage where there's no change in cost, which means you kind of hit the minima, or there is no change in weights, which means you've hit that valley that we keep talking about, right? So once you hit that valley, there's nowhere to go. You're stuck in that valley. So that's where you stop. There is much more to this when it comes to the algorithm as to when to stop, so on and so forth. Unless you start coding and start playing with the data, you will not appreciate it. So strong recommendation, you can simulate your data and then try figuring out the cost and then the lowest cost. If you do that, then you'll understand various issues that are, that are typically that typically affects the optimization. All right. Any questions so far? All right. Let me plunge into multinomial logistic regression. Thankfully, now that you know the binary logistic regression, where you're looking at two classes, positive, negative, good, bad, so on and so forth, for instance. In the multinomial world, what we're doing is we're going to deal with more than two classes. So one example is, so if you're figuring out the sentiment, let's say, so you can classify sentiment as a positive, negative, or neutral. And then let's say you have a sentence and you want to categorize words and designate it as part of speech. So it could be a noun, it could be a verb, it could be an adjective, adverb, preposition, so on and so forth. So these are classic examples where you're dealing with more than two classes. We'll come to the function a little later, what function we're going to use. For the binary case, we were using the sigmoid function. For more than 2 classes, there's another function that we shall use. We'll come to that a little later. But let's look at the characteristic of this function. What is it that is needed? So let's say I have a document and I'm classifying the document into 3: positive, negative, and neutral. So I think one thing is evident. Given the document, the probability of the document conveying a positive sentiment plus the probability of the document conveying a negative sentiment plus the probability of the document conveying a neutral sentiment should be equal to 1. I think that's evident because there's nothing else that the document can convey, right? Given a document, either it has to convey a positive sentiment or a negative sentiment or a neutral sentiment, right? So we're going to generalize this. So let's take a vector z comprising of k arbitrary values, z1, z2, all the way up to zk. So for example, z1 could be noun, z2 could be verb, z3 could be adjective, z4 could be adverb, z5 could be preposition. We need a nice looking function which has to do the following. It has to figure out a probability distribution such that, so of course you have a bunch of features, evidently, and then you're trying to classify, say, in this case, parts of speech, for instance, based on some features, doesn't matter what the features are, into these classifications such as noun, verb, adjective, so on and so forth. Now, one thing is evident. Since it's a probability distribution, the probability of Z1 given the document or given the sentence, for instance, whatever it is, should be between 0 to 1. That's evident. Likewise, the same logic applies to Z2, Z3, all the way up to ZK. And all values, when you sum it up, it should be equal to 1. All right, I think that's evident. No rocket science there. Now, what is that nice looking function that will help us do that? So in the world of binary logistic regression, we were using this sigmoid function that squashed your data into the range of 0 to 1. Now, what we're going to do now is we're going to use this function called a softmax. This is an extremely important function because you take any neural network, which is something that we shall delve deep into in the subsequent sessions. You'll find that one layer will have a softmax function. It'll always be there because typically, again, in neural networks, you end up doing some sort of classification. So you will find that we would be using the softmax function. So let's understand what is happening here. So here, as I said, there are k different classifications. First question, is this a positive number? That's my first question. For all k, is this a positive number for all k?
Yes, we see.
All right. Okay, by the way, just to be sure, what is z? I'll make it simple for you so that you understand what z is. So imagine you have features such as x1, x2, x3, x4. Then I can call z as w dot x. All right. Weights, so I have some weights associated with this. I'm calling it w1. I'm calling this w2, w3, w4. All right. So I multiply x into w, x1 into w1 plus x2 into w2, x3 into w3, x4 into w4, and then I can call that as z. Now, just food for thought. So I have features. So let's consider, say, 4 features: x1, x2, x3, x4. And then I have, let's say, 5 classes: z1, z2. Okay, let's say 4 classes. I'll make it easy. Question. Of course, to get to z, I need the weights. Would it be the same weights, or would I assume that the weights could be different? I need some weights, isn't it? Because we know that z is equal to w dot x plus b. I want to keep it simple. I want to keep it z is equal to w x, okay, dot x. I'll add 1 as a feature as well. Okay. Yeah, my question is, we need the weights to get to z. Do we assume that the weights are same for each z, or do we start with the assumption that the weights could be different? If you're saying something, then you'll have to unmute and say that. Come on, folks, think. Any
We
answer is
can
fine.
initialize random weights for each.
Okay, so we don't know.
Features.
So I'll assume that
Yeah.
this weight is W11. I'll call this 21. I'll call this 31, 41. I'll call this 51. Okay. Blah, blah, blah. I'll call this W14, W24, W54. Now, can somebody tell me what is Z1? These are the weights. These are the features. The feature values don't change, right? The feature values remain same. But then I'm using these features to classify into 4: Z1, Z2, Z3, Z4. All right. Technically not Z1, Z2, Z3, Z4. It's some classification, but for the sake of discussion, let's call it that way. All right. My question: how do I write Z1 now?
X1 W11 plus X2 W21.
That's right. X1 W11 plus X2 W22 all the way up to 1 times W. I'm sorry, not 22, 21. Correct? It's just this. These are the weights for Z1, correct? W51. So I can in general I can say this is nothing but the dot product of W. I'm just calling it as W1 dot X. All the weights associated with Z1 are W1, and then I have the features, all these features combined into this vector X. I'm calculating the dot product. Okay. So likewise, I have Z1, Z2, Z3, Z4, each of them being a scalar, correct? Z1 is a scalar, Z2 is a scalar, Z3, Z4. Now somebody, if I take Z1 for instance, what values can Z1 take? Z1 is a scalar, of course, right? What values can Z1 take?
Minus infinity to plus infinity.
Exactly, any value, because this is just some weight and this is some value for a feature. I'm multiplying them, it can be any number. It can go all the way from minus infinity to plus infinity, correct? So likewise, Z2 can also extend from minus infinity to plus infinity. So so on and so forth for Z3 and Z4. All right. Now coming back to this expression. First question. So here K is 4, isn't it? Because there are 4 classes. First question is, why is this? Okay, is this positive? Is this whole expression positive?
SPC.
Why?
Exponential of something will be positive, right? 2.7.
Of course. So exponential of, you raise a number to E, then that number will always be positive, no doubts at all, correct? So evidently this is positive. The next question would be, will this number, will it be between 0 and 1? This expression, numerator by denominator. That's my next question.
SPC.
Why?
Here we are considering exponential of Z1 means we are taking one data point, I would say, if I'm not wrong, divided by the total summation of the total number of data points, which will also include the term exponential of Z of I.
Is it that many data points, or is it, again, we're just taking one data point here, right? When I say data point here, it's the same set of x1, x2, x3, x4, and 1. We're using different weights, that's it. It's not that we're using different data points. It's
okay.
Right, same x, I use different weights to arrive at Z1, Z2, Z3, Z4, correct? So the data point remains the same, doesn't change. I use different weights, but your argument is right. So let's say this is 5. The 5 is also included in the denominator, correct? Because if you look at this expression, this says sigma j equal to 1 to k exponential of zj. So evidently, the 1 in the numerator, whatever value that you get in the numerator, you will also find that in the denominator, and everything else is positive too. So which means this expression will be between 0 and 1. Okay. So in fact, the softmax of the z vector, where z stands for z1, z2 all the way up to zk, is basically calculating this expression for each zi. So if you look at this, the denominator remains the same, nothing changes. If you look at the numerator, it's exponential of z1, exponential of z2, exponential of zk. Now, there's one last condition that we have to satisfy to ensure that all these are probabilities. This summation must be equal to 1, correct? Why? Because that's what the whole thing is all about. These are supposed to be classifications. I have a data point, which is that x vector. This is the probability that the x vector can be classified as, I don't know, say positive, negative, neutral, so on and so forth. But then we also know that this summation has to be 1. Is it 1? If it is, why it is 1? Anyone? Apart from Sandhya? Sandhya has been answering a lot today. Someone else? You understood the question, folks? These are probabilities. I'm calling it a probability. I haven't established yet that it's a probability because there's one criteria that we have to satisfy, which is some of these probabilities have to be equal to 1. My question is, are they equal to 1? The sum of these probabilities.
Yes, we see.
Okay, tell me why.
Just as like the before argument, dividing the single component by the sum of the total component.
Mhm.
So upon summing, it is almost like it is exactly like sum of the total in the denominator divided by sum of total in the denominator.
Exactly. So the way to look at this is look at this denominator, folks. It's the same throughout. Can I write this as exponential of z1 plus z2 plus z3? I mean, exponential of z1 plus exponential of z2 plus exponential of z3 all the way up to exponential of zk, correct? And when I sum it up, I'll find that the numerator is exponential of z1 plus exponential of z2 all the way up to exponential of zk. The denominator will also be the same, so the ratio will be equal to 1. All right. So what we've done here is we've converted. I mean, we have a probabilistic distribution now. So what the softmax function does is it takes a set of features as inputs and converts that into a probabilistic distribution in a multinomial sense. It's not binaries alone. You're dealing with multiple classifications here. That's what the softmax function does for us. So let's take this example and we'll stop with this for today. Forget the one to the left. Let's just focus this bit here. So here are F features, x1, x2, x3, all the way up to F. And let's say you've given we've been given a document, let's say a paragraph, all right? Oh, in this case, it's not a paragraph. It turns out to be very simple. It's a 3-letter, say, phrase, which was dessert was great. Now we're supposed to classify this phrase as one that carries a positive sentiment or a negative sentiment or a neutral sentiment. Okay. Now, of course, we're not getting into the details as to how we'll calculate the weights. It's again a similar algorithm to calculate the weights. We'll again do gradient descent and all that, but that's not the focus here. The focus here is to see how you can formulate the multinomial logistic regression problem in this context. That's the objective here. So there are a bunch of features. In this case, there are only, say, 3 features: word count, positive lexicon words, and count of no. Word count means the number of, so one feature basically counts the number of words, which is 3. And then positive lexicon words are those that carries a positive sentiment. So in this case, great carries a positive sentiment. So that's 1 here. Count of no basically means it just checks if there is this word no that exists anywhere in that phrase. There isn't. So which is why the count of no is equal to 0. Okay. 3 features. So don't worry about how did we come up with these features? That's not the objective here. But let's say you have these 3 features and then you have 3 outputs, y1, y2, y1 hat, y2 hat, and y3 hat. Okay. Now, what we are saying here is all these features can be an input to this classifier, right? So x1 can be an input, x2 can be an input, x3 can be an input. Of course, this diagram has more features, which is why you see xf, but let's just focus on x1, x2, x3. So x1 is an input, x2 is an input, x3 is an input. Likewise, if you look at the next classifier, the negative, you'll find x1 is an input, x2 is an input, x3 is an input. And finally, if you take neutral, again, x1 is an input, x2 is an input, and x3 is an input. If that's the case, what is it that when data moves into this node, And of course, we have to classify that as positive, negative, or neutral. But if you think about it, it's the same x1, x2, x3 values that is coming into this node. So what is it that differentiates this node versus this node versus this node? If it's the same values that are coming,
The weights.
exactly the weights. So, which means when x1 moves into this node, it will carry a certain weight. Likewise, when x1 moves into this node, it might carry a different weight. And likewise, when x1 moves into this node, it will carry a completely different weight. Okay, so the way to formulate this problem is we'll have z1, z2, z3. I'll write z1 as x1, something like w11. Basically, we will have different weights for different classes. And once I have z, so let's say I have z1, z2, z3, I will pass them to the softmax function, because what the softmax function does is, if I have z1, z2, z3 with me, it will help me to figure out probability. That's what we did here. If I have z1, z2 all the way up to zk here, but let's say there is just z1, z2, z3, then what the softmax function will do is it will help us to figure out probabilities, right? So what I can do is, assuming I have the weights with me, I have the x with me, then I can apply the softmax function to figure out the probability of this data, dessert was great, conveying a positive sentiment or a negative sentiment or a neutral sentiment. Since, I mean, just for the sake of discussion, since we know that dessert was great is certainly a positive statement, what you might end up finding is probability of positive could be like 0.7. The probability of negative could be say 0.2, and the probability of neutral could be 0.1. So what would you do? You would say, okay, since the probability of the data conveying a positive sentiment is the highest, I shall classify this as positive, so on and so forth. Okay. Any questions here? None? All right. If there isn't any questions, we'll stop here for the day. This would be the last session on logistic regression. So our plan of action would be we will move to vector semantics from the next session. So the whole idea is to figure out ways to convert words into vectors. So we'll do some basic count-based approaches, and that's the basic stuff. And then we'll start doing some neural networks, because one key approach towards converting a word into a vector, the one that carries a sentiment, is, it makes use of neural networks. So we'll touch upon neural networks, and then we'll also try to understand one algorithm, which is the word to vec, if I'm right, algorithm. It's a bit involved, so we'll have to take a while to understand how that algorithm works. And then once we've done with that, we'll continue with our journey where we dig deep into neural networks. Any questions? Just to be sure, if there are any. Okay. If there isn't any, thank you for joining. Have a good night and catch you on Monday.